In the veritable magnanimity of scientific goulash that is general chemistry, I now continue part 2 of our 2-video lecture about matter and measurement, the blocks that move.
If you like building blocks or know someone who does, you're going to want these. The flexi blocks, the blocks that move.
After this lecture, you should be able to make calculations using the proper number of significant figures, know how to use dimensional analysis to interconvert between different units, and be able to interconvert between mass and volume using density. But first, I'd like to share with you a funny story. One slightly humorous mistake made by NASA occurred some time ago when a private subcontractor they hired used pounds, which are American English units, instead of newtons, which are SI units. The following paper from Popular Science summarizes this event as follows. Quote, "The brains of the 1998 Mars missions, NASA intended the MCO, the Mars Climate Orbiter, to serve the dual function of studying the Martian atmosphere and relaying radio signals from 2 surface probes. The problem: in one of the all-time great engineering gaffes, NASA subcontractor Lockheed Martin created thruster software that used imperial units, not the metric units used by NASA. NASA did not know this, never converted from pounds to newtons, and the probe eventually hit the atmosphere at the wrong angle and burned up. One of the saddest things about this mistake was that it probably wasted millions of taxpayer dollars. Karnsarnet. We can learn from this, however, that it's not only important to know how to use proper unit conversions, as I will teach you later in this lecture, but also to use the proper units to begin with. Now, in measuring things, there's always at least some uncertainty in the last integer of any measured value. So when we take values we've measured and then multiply, divide, add, or subtract them from each other, the uncertainty built into each individual value will compound together as you multiply, add, subtract, or divide it with another value, which ends up making the final answer even more uncertain. So to avoid this sort of exponential increase in uncertainty, we follow special rules called significant figure rules. So here's my summary of significant figure rules. First, we have to know how many significant figures a value actually has. To do this, we read the number from left to right, starting with the first digit that's not 0. We then remember the following. 1. Zeros that are between non-zero digits are always significant. For example, the value 1,005 kilograms has 4 significant figures because these zeros are between 2 non-zero integers. The value 7.03 has 3 significant figures, so this 0 does count as a significant figure. Rule 2, zeros at the beginning of a number are never significant. So this value right here, 0.02, only has 1 significant figure. This 2 is the only integer that is a significant figure. These zeros to the left of it are not significant. Same thing with this value right here. 0.0026 only has 2 significant figures, the 2 and the 6. Rule 3, zeros at the end of a number are significant if the number has a decimal point. For example, in this value, 0.0200, this has 3 significant figures. The zeros that are to the left of the 2 are not significant because of rule number 2. However, the zeros that are to the right of the 2 are because of this rule number 3. Similarly, this value, 3.0 centimeters, has 2 significant figures. Both the 3 and the 0 are significant. The 0 because it is to the right of the 3 and after the decimal point. So this brings us to our first problem. Which of the following has the same number of significant figures as the number 1.00310? In order to answer this, we have to first determine how many significant figures this value actually has. 1.00310 has how many significant figures? Well, as we look at it, these 2 zeros, the ones between the 1 and the 3, we ask ourselves, are they significant? Well, according to Rule 1 from our previous slide, they are, because they lie between 2 non-zero integers. What about this final 0 at the end? It lies to the right. Is it significant? Well, according to rule number 3 from our previous slide, it is, because it is in a value that has decimals. So this number right here has 1, 2, 3, 4, 5, 6 significant figures. With that said, we now are going to look at all of the options that we have and select the one that has also 6 significant figures. How many significant figures do each of these numbers have? Option A only has 1. Option B has 6. Option C has 3. Option 4 has 4. And option 5, how many does that have? Well, option 5, or option E, I should say, only has 1 significant figure. Because there's no decimal in this number, the zeros that appear to the right of the 1 are not considered significant. Hence, the correct answer is B. Let's see if we can navigate our way through this problem. The number with the most significant zeros is what? I'll let you answer this question on your own. You can, of course, consult the previous slide that I shared to do so. So now that we know how to determine the number of significant figures in a value, we next need to learn how to carry these through properly when doing mathematical calculations with them. As it turns out, there are different rules for adding and subtracting than there are for multiplying and dividing. Thus, when adding and subtracting values from each other, our answer should have the same number of decimal places as the value that has the fewest decimal places. When the answer contains more than the correct number of significant figures, it has to be rounded off. We can see that in this example. Here's an addition problem. I'm adding these 3 values together to get this final answer. The question is, how do I appropriately express that final answer using the correct number of significant figures? Remember, when we're doing addition or subtraction, the final answer has to have the same number of decimal places as the value that had the fewest decimal places. You'll notice that this first value has 2 decimal places, this second value has 3 decimal places, and this third value has 1 decimal place. Because of that fact and this rule, when we add these 3 values together, the final answer has to be rounded off so that it also has only 1 decimal place. Hence, this final answer gets rounded off to be 104.8. Does that make sense? Good. Let's do some problems. Here's a lecture question. Report the answer to the following calculations to the correct number of decimal positions. Assume that each number is plus or minus 1 in the last decimal position reported. And here's another one. Carry out the following operations and express the answers with the appropriate number of significant figures. Now, I think in order to address these, or at least help you in addressing them, this would be best done by looking at the doc cam. So I'm going to just tackle a couple of the examples from these problems. One of the questions that I wrote down says 685 minus 595.325. Now when I punch that into my calculator, the answer that I got is 89.675. Now, because this is an addition or subtraction problem, in order to report the answer with the proper number of significant figures, I have to report whatever answer has the same number of decimal places as the value that had the smallest number of decimal places. In this case, we see this has 0 decimal places and this one has 3 decimal places. Hence, the answer has to have 0 decimal places. In order to do that, I'm going to round up to 90 because 6 rounds this number to 90. So that is the final answer for that one. In a later example that I gave, we see the number 952.7 minus 140.7389. When I punched that into my calculator, the number that I ended up getting was 811.9611. Once again, this is an addition-subtraction problem, so I have to report my answer with the proper number of significant figures, which is going to have the same number of decimal places as the value that had the smallest number of decimal places. You'll note that this has 1 decimal place and this one has 4. So the answer that I'm going to be doing will have to have 1 decimal place.
If I round this position up from this 6, it ends up rounding the entire value up to 812.0.
Now, as I mentioned before, there are different rules for adding and subtracting than there are for multiplying and dividing. Thus, when we multiply or divide values, our answer should have the same number of significant figures as the value that had the fewest significant figures. When the answer contains more than the correct number of significant figures, it has to be rounded off. We can see that in this example. So here I've got a problem where I'm multiplying two values together, 6.221 by 5.2, and I get this final answer in my calculator. So the question is, how many significant figures do I have to express in my final value? Because this is a multiplication operation, I have to follow the rule for multiplication, which is the same as the rule for division. The final answer has to have the same number of significant figures as the value that had the fewest number of significant figures. So as we look at these two values, 6.221 has 4 significant figures, but 5.2 only has 2 significant figures. Hence, I have to round off my final answer so that it also has 2 significant figures. So this final answer gets rounded off to be 32. Does that make sense? I hope so. Let's do some problems. Our next lecture question says, report the answers of the following calculations to the correct number of decimal positions. Assume that each number is plus or minus 1 in the last decimal position reported. Now keep in mind, these are multiplication and division questions, so they use their rules as opposed to the rules for addition and subtraction. Here's another question. Carry out the following operations and express the answers with the appropriate number of significant figures. Now once again, as with our previous examples, these are probably best answered by looking at the DocCam.
For this next section of questions, one of them states that we have to multiply 685 by 595.325 and report our final answer with the proper number of significant figures. When I throw this into my calculator, I end up getting 407,797.625. Because this is a multiplication question, I have to report my answer so that it has the same number of significant figures as the value that had the least number of significant figures. You'll note that this value has 3 and this one has 6. Hence, my final answer should have just 3 significant figures. So I'm going to round that to 408,000. That number only has 3 significant figures because you'll remember from our significant figure rules that zeros that are to the right do not count as being significant unless they are after a decimal place. Another way of writing this would be if we were using scientific notation style, 4.08 times 10 to the 5th. That also only has 3 significant figures. Another problem that we gave later on was 0.0588 divided by 0.677. This is a division problem, of course. So once again, the answer has to have the same number of significant figures as the value between these two that had the least number of significant figures. When I throw this into my calculator, I end up getting an answer that looks something like this, 0.08684. Now looking at this, you'll remember from our significant figures that zeros to the left of non-zero integers do not count as significant. So these two zeros do not count as significant, and neither does this one. Hence, both of these values have 3 significant figures. So I'm going to need to report my final answer as having just 3 significant figures. One way of doing that is to report it as being 0.0869, or if I want to use scientific notation, I could report this as 8.69 times 10 to the negative 2.
We now change to a new and extremely important subject, interconverting between different units. This process is also called unit analysis or dimensional analysis. Basically, whenever we're given a value, such as the depth of the human colon, for example, in specific units like meters, and we're asked to convert it into different units like yards, we have to follow certain steps. Here are those steps. 1. Write down the value that you want to convert. This is usually the value that has no units in its denominator. 2. Draw a set of parentheses to the right of it with a horizontal line in the middle. 3. Write units, no numbers yet, that relate to each other on the top and the bottom of the horizontal line that you just drew, that will cancel out the units you started with and leave behind the units that you want to convert to. Multiple sets of parentheses may be necessary. 4. Now put numbers on the top and the bottom of each set of parentheses that go with the units in that set of parentheses. As you do so, make sure that each set of parentheses with numbers and units convey a true statement. And 5. Multiply all the numbers out using your calculator. This should cancel out the units you started with and arrive at the unit that you want to convert to. Complete with the correct numerical answer. Express your answer with the correct number of significant figures. Now, I realize that these steps I've just navigated through probably don't mean anything to you at this point. Please don't freak out. I promise that they will momentarily as we work through some examples. In other words, are you confused? No problem. Let's do an example. This comes from our problem set. Question number 20. The lung capacity of the blue whale is 5.0 times 10 to the third liters. Convert this into gallons. How in the world do we do that? Well, remember, we follow the steps that I just delineated in the previous two slides. Whew. Step 1. Write down the value that you want to convert. In this particular problem, that value is 5.0 times 10 to the third liters. Okay, no problem. Step 2. Draw a set of the parentheses to the right of it with a horizontal line in the middle. Here's how we do that. We just kind of manually draw this to the right of our original value. Done with step 2. Step 3. Write units, no numbers yet, that relate to each other on the top and bottom of the horizontal line, that will cancel out the units you started with and leave behind the units you want to convert to. In this case, I'm going to put liters at the bottom of the fraction to cancel out the liters that I started with, and then I'll put gallons, which is the unit that I want to convert to, on top. When I do this, I have to make sure that the two units, liters and gallons in this case, can be related to each other numerically. Now I know that they can, so I'm good. So here's what we've got. We have our set of parentheses, and I'm basically putting liters on the bottom and gallons on the top. Now when I do this, I look at it and I ask myself the question, do liters and gallons relate in some way using a number? And as it turns out, they do. 1 gallon equals 3.785 liters. Step 4. Put numbers on the top and the bottom of each set of parentheses that go with the units in that set of parentheses. As you do so, make sure that each set of parentheses with numbers and units conveys a true statement. In this case, we know that 1 gallon equals 3.785 liters. So I'm going to put 3.785 on the bottom and 1 on the top like this. Now that I've written in the numbers, I ask myself, here's this expression. Is the expression that I've written actually true? In this case, are there really 3.785 liters in 1 gallon? Is that true? Well, if so, then my parentheses are written correctly. If not, then I need to rewrite them until I have a true statement in those parentheses. The reason that I emphasize that is because I sometimes see students switching the numbers around and accidentally writing 3.785 gallons in 1 liter, and that would be an incorrect statement. So I always want to make sure I put the numbers in the correct place. Step 5. Now that I have this all written out, I'm going to multiply it through using my calculator. If I've set it up correctly, all my units should cancel out and leave me the units that I want to convert to. You'll notice that liters cancel out liters in the denominator, and as I multiply this through with my calculator, I end up getting 1.3 times 10 to the third gallons. Now, the final step is, of course, to express the final answer using the correct number of significant figures. We've actually discussed this already. You'll note that there are 2 significant figures in the original value, 4 in this measurement here, and because this is a multiplication problem, I'm going to end up with 2 significant figures in my final answer. So this answer, as expressed, is correct. Does that make sense? Good. Let's go ahead and do some more examples. This first one comes from our problem set. A bumblebee flies with a speed of 15.2 meters per second. Calculate that speed in kilometers per hour. Note that 1 hour is 3,600 seconds. Next lecture question. The Statue of Liberty is 151 feet tall. Convert this to meters, and note that 1 meter is about 3.28 feet. And the last lecture question on the slide, the speed of light in a vacuum is 2.998 times 10 to the 8th meters per second. Convert it to miles per hour, noting that 1 mile is 1609.344 meters, roughly. Now I realize that I can't just throw these at you and expect you to do them. I'm going to go ahead and do 1 or 2 of them on the doc cam.
We'll take a look at this first example in which we are told that a bumblebee flies at 15.2 meters per second, and we're asked to convert that into units of kilometers per hour. How in the world do we do that? Well, you will remember my steps delineated for doing dimensional analysis. Step 1 is write the value that you're given that you want to eventually convert into something. Step 2 is draw a set of parentheses to the right of it. Step 3 is put units, not numbers, into those parentheses so that you will cancel out the units you start with and end up moving toward the units you want to go to. In this circumstance, I'm going to go ahead and place meters in the denominator so that it will cancel out my meters in the numerator. You'll note that I'm wanting to eventually get to kilometers per hour. Now, there's no direct way to relate meters to hours, but there is a way of directly relating kilometers to meters, so I'll go ahead and put kilometers in the numerator. You'll note that we are going to cancel out our meters and end up with kilometers in the numerator. But that still doesn't get me to kilometers per hour because I still have this seconds in the denominator. What do I do? Well, what I'm going to do is add another set of parentheses. I can put seconds in the numerator, and that will cancel out my seconds in the denominator here. And I'll put hours in the denominator, noting that there is a direct way of relating seconds and hours. We'll go ahead and throw in numbers, which is the next step. How do meters and kilometers relate to each other? In every 1 kilometer, there are 1,000 meters. Now that I've put that number down, I always step back and ask myself the question, does that make sense? Have I put the numbers in the correct place? Are there indeed 1,000 meters in every 1 kilometer? Or in other words, does 1 kilometer contain 1,000 meters? That seems correct to me as I sort of think about it in my brain, so I'm going to move on. How about seconds and hours? Well, as it turns out, 1 hour has 3,600 seconds in it. I put the numbers down, make sure that I've put them in the right place. The reason that I tell you to do that is because I've seen so many students put these numbers in the wrong place, where they put the 1 on the top and the 3,600 on the bottom, and they get the wrong answer. Don't do that. Put the numbers down and then step back and ask yourself, did I put the numbers in the right place? You can imagine if I put a 1 on top and 3,600 at the bottom, me asking myself the question, does 1 second contain 3,600 hours? No, that seems absolutely ridiculous. That way I can logically reason my way toward putting the numbers in the proper place. Now that I have all of these numbers in the proper location, I go ahead and multiply them through with my calculator. You'll note that all of my units have canceled out, leaving me kilometers per hour. The final numerical answer that I end up getting when I throw these into my calculator is 54.72. Now, I need to be sure to express my answer with the proper number of significant figures. Because this is a multiplication question, my final answer has to contain the same number of significant figures as the value that contained the least number of significant figures, which is 15.2. 3 significant figures, so I'm going to go ahead and round. So my final answer is going to be 54.7 kilometers per hour. Another question that we had written here was converting the speed of light, which is 2.998 times 10 to the 8th meters per second into miles per hour, I believe. So once again, step 1 is write down your value. Step 2 is put a set of parentheses here. Step 3 is start writing out units. I want to eventually move towards miles per hour. So, We'll go ahead and put meters in our denominator so that it will cancel out our meters in the numerator. Is there a way to directly relate meters and hours? Probably not, but there is a way to directly relate meters and miles, so I'll write miles on the top. So far I've canceled out my meters and I end up with miles in my numerator, but I need to end up with hours in my denominator. The only way of doing that is adding another set of parentheses. If I throw seconds in the numerator and hours in the denominator, you'll note that the seconds cancel each other out, and I indeed end up left with the units that I want, which is miles per hour. Now I go to my next step, which is insert numbers. Let's make sure that we insert numbers correctly. We are told that 1 mile contains 1,609.344 meters. Now that I've put the numbers down, I ask myself the question, does that make sense? Did I put the numbers in the proper place? Can I imagine there being about 1,600 meters in 1 mile? Yeah, that feels about right. So let's move on. We've noted from our previous example that there are 3,600 seconds in 1 hour. That seems to be in the right place. So you'll note that I've canceled out all the units that I started with and ended up getting to the units that I want to end up with. As I throw that numerically into my calculator, the final answer that I end up getting is 670,635,167 miles per hour. Now, of course, we need to report our final answer with the proper number of significant figures. Because this is a multiplication problem, that answer has to contain the same number of significant figures as the value that contained the lowest number of significant figures. As we look through here, we'll note that this is 4 significant figures. This is, 7 significant figures. This looks like it contains 4 significant figures. In reality, that actually contains infinity significant figures. The reason is because it is a perfect value. There are indeed exactly 3,600 seconds in 1 hour. Anytime you have an exact value, its number of significant figures is infinity. These, however, are not exact values. They are rounded values. So my value that has the lowest number of significant figures is this one, which is 4. So I'm going to go ahead and convert this into a number that has 4 significant figures, which I could round to being this. That number only has 4 significant figures. If I want to express it in scientific notation, I'm going to rewrite it as being 6.706 times 10 to the 8th miles per hour, assuming that I've done my calculations correctly anyway.
We now arrive at another subject, density. You see, if you want to convert between 2 different mass units, such as converting from grams to pounds or something like that, it's really, really easy. You just go through the process that we just went through. But what about converting between mass of something and its volume? Now, there isn't a direct way of converting from mass, like grams to liters. You can't do that quite as easily as you can convert from grams to pounds. So how in the world do I do this? Well, to do this, I have to use density. Density is the thing that lets me convert between mass and volume. Density.
Lorraine, my density has brought me to you.
What?
Oh, what I meant to say was...
Wait a minute. Don't I know you from somewhere?
Yes, I'm George McFly. I'm your density. I mean, your destiny.
And what is density? Well, density is the substance's mass divided by its volume. For example, you could imagine me having a big piece of metal, and it takes up a certain volume, and if I had a piece of styrofoam that took up the same volume, which one would be heavier? Well, the metal, obviously. The metal weighs more in the same volume weighs more than styrofoam. So I could surmise then that metal is denser than styrofoam, because in the same volume, if I have the same volumetric amounts, the metal is going to have more weight. I hope that makes sense. So density is once again the weight or mass of something in a certain volume. Now, does that feel okay? Good. Let's go ahead and do some problems. Next one from our problem set, osmium has a density of 22.6 grams per cubic centimeter. What volume would be occupied by a 21.8 gram sample of osmium? In order to do this one proper, we're going to do it on the DocCam.
In this really enjoyable problem set question, which I absolutely love, we're given the density of osmium and we're asked to calculate the volume that would be occupied in a 21.8 gram sample. Step one is I take the value that I'm given that I want to convert, 21.8 grams. Now I realize that one thing that confuses students is when they're given multiple values in a question, knowing which one to pick. Sometimes you just have to practice to figure that out. Usually it's the value that has no denominator units. Now that is not always the case, as we've seen in some previous examples today, but it happens to be the case here. So I want to figure out in a 21.8 gram sample, what is the volume that would occupy for osmium. I'm given the density, and the density is given in grams per cubic centimeter, and it asks me to calculate the total volume in cubic centimeters. So indeed, that is the only value that I need to use to make this conversion. The next step that I have to do is make sure that I put in my proper numbers. It tells me that there are 22.6 grams in 1 cubic centimeter for osmium. That is osmium's density. Now make sure that we put those numbers in the proper place. It says that there are 22.6 grams per cubic centimeter. So you wouldn't want to put 22.6 on the top and 1 on the bottom, because that would be wrong. That would be saying there's 22.6 cubic centimeters in a gram, and that is not right. So whenever I put my numbers in there, I always make sure that I put them in the proper place. You'll note that the grams cancel each other out. I end up with cubic centimeters, and numerically the answer ends up being 0.96460. But once again, this is a multiplication problem, so the proper number of significant figures had better match the value that contains the lowest number of significant figures, which in this case for both values is 3. So I'm going to go ahead and convert that to 0.965, which if I do in scientific notation is 9.65 times 10 to the minus 1 cubic centimeters.
Next lecture exercise, what is a mass in kilograms of 15.6 gallons of gasoline, given that density? I'm not going to answer that one for you. I'll let you see if you can tackle it on your own. Another one from our problem set, an individual with high cholesterol has 242 mg of cholesterol per 100 milliliters of blood. If a person's total blood volume is 5.2 liters, how many grams of cholesterol does the person's body contain? Now, I'm not going to answer either of these questions for you. I'll let you attempt them on your own. And our last question, the density of air, atmospheric pressure, at 25 degrees Celsius is 1.19 grams per liter. What is its mass in kilograms in a room that measures all of those numbers in feet? I think in order to be able to tackle this one properly, we should do it on the DocCam.
In our final problem, question number 25, we are given the density of air as being 1.19 grams per liter, and we're asked to calculate what the mass would be of a volume of air that occupies a room measuring 14.5 feet by 16.5 feet by 8.0 feet. Now the challenge here is we need to be able to calculate what that actual volume is in total. If you take 14.5 feet and multiply it by 16.5 feet, multiply that by 8.0 feet, you end up getting a total volume of 1914 cubic feet for that room. Now, in order to properly do this, I need to remember the total number of significant figures that I end up using here is going to equal, I'm going to go ahead and pause on that. So here's a volume of a room, 1,914 cubic feet. The question is, what is the total mass of the air that occupies that room? I'm going to have to do dimensional analysis. I begin by writing down 1,914 cubic feet, and I'm going to put a set of parentheses. Now remember, I want to end up getting at the end an answer that that is in grams. That is a mass unit. So what in the world am I going to do here? Well, I need to cancel out my cubic feet, so I'll go ahead and put that in the denominator. But what do I put in the numerator? You'll note that in the problem we are given a relationship between cubic feet and liters. So I can actually put liters in the top. If these cancel each other out, have I arrived at grams yet? I haven't. So that means I'm going to have to put another set of parentheses here. Now obviously I'm going to put liters in the denominator so that I can cancel out the liters in the numerator here. But what do I put in the numerator over there? What in the world can I put there? What have I been given? I have been given grams. So what we'll do right there is go ahead and throw in those values, and then we'll throw in our numbers next. I've been told in this problem that in 1 cubic feet, there are 28.317 liters. I've also been told in this problem that for air, there are 1.19 grams in 1 liter. Have I put all of my numbers in the proper place? Yes, I have. If I pump this through my calculator, the final answer I end up getting is 64,496.5 grams. Now, obviously, I need to make sure that this final answer is expressed with the proper number of significant figures. You'll note, however, that as I look back at all of the values that I was originally given in this multiplication problem, the value that had the smallest number of significant figures was that one. It only has 2. Everything else had 3 or more. Hence, my final answer had better be expressed with only 2 significant figures, which, if I round, is 64,000 grams. Now, if I want to, I can go ahead and convert that into scientific notation, which is 6.4 times 10 to the 4th grams.
I now end with some example questions just for you to practice interconverting between different units. First one, how many seconds are in a day? Next one, how many hours in a year? Next one, if you're going 50 miles per hour, how many feet per second are you traveling? That brings us to the end of this lecture and the end of our chapter coverage of mass and measurement for our general chemistry intro. I hope that you're enjoying it, and I hope that you look forward to our next lecture, which will start Chapter 2's discussion on atoms, molecules, and ions. Until then, have an enjoyable rest of your day.